So in this video we're going to show an example of converting from spherical to rectangular equations. And in the example what we're going to see is that the list, this kind of the standard list of conversion relationships that we established aren't quite going to be enough to get us where we need to go. And it's going to make sense to look at and think about the geometry of a spherical coordinate system. So it says find a rectangular equation for rho equals cosecant of phi. And when we're doing these, there isn't like a right way to do it. And a lot of it's just experimenting and pushing things around until you find something that works. So when I look at this and I see I've got the cosecant of phi, and I see that my pile of relationships that involve phi all have sines and cosines, that kind of leads me to want to get this spherical equation rewritten in terms of sine of phi or cosine of phi. And what I'm going to do is multiply both sides by the sine of phi. So I'm going to go rho sine phi, multiply the left hand side times the sine of phi. And I'm going to multiply the right hand side by the sine of phi, but the cosecant function is the reciprocal of the sine function. So when I take the cosecant of phi times the sine of phi, I just get a 1. When we take the product of reciprocals, we get 1. And then when I look at this, I have a rho sine phi, which looks kind of good because I have rho sine phi here. I have rho sine phi here. So some things that would make sense to try that, but that might push us in kind of a circular direction, would be, hey, multiply both sides by the sine of theta, so you get a y on the left hand side, or multiply both sides by the cosine of theta, so we get an x on both sides. That could lead us a little bit in the direction of chasing our tails, but those would be sensible things to experiment with. And a lot of times when you're doing these conversions, that's what you're doing. You're experimenting with the relationships that you have, trying to find something that works and comes out nicely, that eliminates all of the spherical coordinates and leaves you with just an x, y, z kind of thing. So sometimes when you get something like this where you have rho sine phi, it makes sense to draw the spherical coordinate system. And so this is the one that this is the illustration we used in previous videos. And in those videos we changed this r to rho to kind of match our standard calculus textbook. And we called this distance right here r. So this forms a right angle here. And then one of the things that we did is we took this line segment here and we lifted it up and said, hey, there's a corresponding line segment up here that goes out to our point, and this distance is r. So we formed a rectangle where rho is the diameter of that, or the diagonal, sorry, of that rectangle. And this is a right angle right here. So when I look at this, my hypotenuse is rho and my side opposite phi is r. So from trigonometry, that tells me that r equals rho times the sine of the angle phi. That's directly from trigonometry. R over rho equals sine of phi. Multiply both sides by rho to get r equals rho sine phi. So I could replace this with r. And at first that maybe doesn't look like that is very useful, except we know what r is. We have worked out in previous videos, both working with polar and cylindrical coordinate systems, we've worked out that r is just equal to x squared plus r squared is equal to x squared plus y squared by the Pythagorean theorem. So if I know this length r and I know what r squared is, let's just go ahead and square both sides here. We'll get r squared equals 1, and then I can replace r squared with x squared plus y squared, and now I have a rectangular equation for my spherical equation. So I wound up having to move through this intermediate piece where the relationship I really wanted was the relationship between rho sine phi and r, which wasn't necessarily our standard, listed as part of our standard relationships. So being able to draw the geometry of the spherical coordinate system can help you with things like this, where maybe the thing you need isn't exactly showing up in the list of relationships, but we can still work through the geometry of the problem. And then what we'll notice here is the z coordinates missing. So we actually have a cylinder. This is a circle of radius 1 centered at the origin in the xy plane. And because the z-axis is missing, right, this would be the xy plane. If we were thinking about what the graph of this is, if this is the xy plane, here's a circle in the xy plane, but we are in three-dimensional space. So if we extrude out our z-axis, we'd have a cylinder pulling out parallel to that z-axis, and it'd be a right circular cylinder. That cylinder would be perpendicular or orthogonal to the xy plane.